Ohm's law. In previous videos, we have covered the basic quantities in electricity. In this one, we're after one thing: relationship. And Ohm's law is a perfect tool for us to relate voltage, current, and resistance. Here are the key concepts for our video. You can see that it's all about relationship. After this video, you should be able to express each quantity in function of the other two, show how current responds to changes in voltage and resistance, and use graphs to express your ideas about voltage, current, and resistance. In this circuit configuration, we have a complete one-loop circuit. We have the voltage source here, the path for current, and the load, which is our resistor in our case. The new device here is going to help us measure current. It's called an ammeter, and on the left side here we have low values for current. On the right we have high values. Notice that it's connected in the current path, so current to be measured goes through it. Our circuit loop is closed, current is flowing, and here is our current value reading on our ammeter. Now we want to increase voltage here. Remember that voltage is a tendency for charges to move. If we increase this tendency with the circuit loop closed, more charges are going to flow in the circuit path. More charges means more current. More current means this needle here to move right, and this needle moving right means more current. So more voltage means more current in the circuit. If we increase voltage again, our needle is going to move more to the right, meaning that current has increased. From this analysis, we understand that an increase in voltage results in more current flowing in the circuit. If we try and use graphs to express our ideas here, we come up with a graph like this. This is voltage. This is current. Let's say this is voltage 1. Voltage 1 results in current 1 flowing in the circuit. We increase voltage by this value, we get voltage 2, and current 2 flows in the circuit. This is how we use graphs to display this relationship between voltage and current. Current has increased up to this value in the circuit. Now we want to decrease voltage to see what happens. Let's do that. We decrease voltage to V2. This means that the tendency for charges to move is going to decrease, meaning that less charges are going to flow in the circuit. Our needle here is going to move left, telling us that current has decreased. Let's say it decreased to I2. From this we understand that a decrease in voltage results in less current flowing in the circuit. I want you to be able to relate what happens in the circuit to what we see in the graph here. The horizontal line here represents voltage, and voltage increases in this direction. The vertical one is current, and current increases in this direction. With this in mind, our V2 should be somewhere here, and the resulting current will be I2. If we decrease voltage again, let's say we decrease it to V1, less charges are going to flow in the current path. Our needle is going to move more to the left. Current is going to decrease to I1. So how do you represent I1 on the graph? First, represent V1 and I1 is here. Now we focus on this resistor. We keep the voltage constant. The circuit is closed and current is flowing. What happens if we increase the resistance? More resistance means more opposition to current. More opposition means less current flowing in the circuit, and our needle here is going to move left. From this, we understand that more resistance in a circuit causes less current to flow in the circuit. A decrease in resistance, however, means less opposition to current. Less opposition to current means more current flowing. Our needle here is going to move to the right. From this, we get that a decrease in resistance causes more current to flow in the circuit. If we use a graph to describe the behavior of our circuit, we get something like this. We can see that as resistance increases, current decreases. For instance, if we have R1 here as resistance, we get this current value, I1. But if we go here and say we have R2, the value for current is I2, which is less than I1. The curve we have here is different from the one we have found before because they are two different functions. The first one was current as a function of voltage. This one is current as a function of resistance. And we explained this by Ohm's law. Ohm's law states that current increases with an increase in voltage but decreases with increase in resistance. And another way to say that is that current equals voltage divided by resistance. From this formula, you see that if you increase voltage, current increases. We suppose that resistance is constant here. If you decrease voltage, current decreases, and that's what we have found. If we keep voltage constant and increase resistance, current is going to decrease. We decrease resistance, current is going to increase, and this is exactly what we had. The relationship here explains why these two curves are different. The first one is current as a function of voltage, and if we compare it to what we used to see in mathematics, it's like y equals ax function. The second one, current as a function of resistance, it's like y equals a divided by x. Now you know to use Ohm's law to compute current. But what if you want to compute voltage? If you use simple algebra, we get that voltage equals resistance multiplied by current. Again, you might want to compute resistance. Resistance equals voltage divided by current. And you should remember the units here. Now is the time to recap. Ohm's law states that current equals voltage divided by resistance. We can use graphs to describe behaviors we have found in circuits. The first graph here is current as a function of voltage. We can compare it to the function we are used to see in math, y equals ax. The second one is current as a function of resistance, and we can compare it to another function, y equals a divided by x. And you can use Ohm's law to compute current, voltage, or resistance. I hope this has been informative to you, and I'd like to thank you for viewing.